This is Kruti Jaipancholi, Assistant Professor in LGA Institute of Engineering and Technology in Department of Electronics and Communication. So friends, this video is about fiber optic communication. So friends, in the last video, we discussed about the quantum efficiency, internal quantum efficiency, external quantum efficiency and related power. From this video, you will learn about the injection laser diode ILD and Fabry-Perot Resonator. So friends, what is the ILD? The ILD, that is the injection laser diode. As we know that there are the two light source elements that can be used. So that are the LED and the laser. In this video, we will discuss about the ILD and specifically the Fabry-Perot Resonator. So laser is a device which amplifies the light. Hence, the laser is the acronym for the light amplification by stimulated emission of radiation. So that's a full form of the laser. Now, what is the operation of the ILD? So the operation of the device that may be described by the formation of electromagnetic standing wave within a cavity, which is known as the optical resonator, and which provides the output of a monochromatic highly coherent radiation. So this way the ILD that operates. The principle of the ILD, that is the material which absorbs the light, then the emitting. Three different fundamental processes that occurs between the two energy states of an atom. So now that three processes are: the first process is which is known as the absorption. Second is the spontaneous emission. And third one, that is the stimulated emission. So, this way, the laser action, that is the result of three processes: absorption of the energy packets, spontaneous emission and the stimulated emission. Now, the energy level diagram. Here you can see that the E1 energy level and the E2. Okay. And by applying the energy, the atom that reaches to the final state. So E1 is the lower state energy level and E2 that is the higher state energy level. So the very first process, that is the absorption process. So in the absorption process, the atom that will reach to the final state by providing the energy to them. So, the quantum theory states that any atom exists only in a certain discrete energy state, that is by the absorption or the emission of the light, that causes them to make a transition from one state to another state. And the frequency of the absorbed or the emitted radiation F, that is related to the difference in energy E between the two states. Okay, so now if the E1, that is the low state energy level and the E2 is the higher state energy level. So now E is equal to E2 minus E1 and we can write that this is equal to H into F, where H is 6.626 multiplied by 10 raised to minus 34 joule per second. It's a Planck constant. This H is known as the Planck constant. Now, atom is initially always at the lower energy state. Now, when the photon with the energy E2 minus E1, that is incident onto the atom, this will be excited into the higher energy state E2 through the absorption of the photon, as we have seen into the energy level diagram. Now when the atom, that is in the first process by the absorption, atom is in the higher energy state, E2. It can make a transition to the lower energy state even by providing the emission of a photon at a frequency corresponding E is equal to H into M F. So this emission process can occur in two ways. That is by the spontaneous emission, in which the atom returns to the lower energy state in a random manner. So here in the diagram you can see that how the atom that reaches to the again the lower level. So this process, that is returning into the lower energy state in a random manner, is referred to as a spontaneous emission. Now in the emission process, it gives the incoherent radiation. Now the next is about the by stimulated emission. Now when a photon having the equal energy to the difference between the E2 minus E1 that interact with the atom, causing it to the lower state with the creation of the second atom. So this is known as the stimulated emission. So the spontaneous stimulated emission. Stimulated, that gives the coherent radiation. Spontaneous, non-coherent. So hence the light associated with this emitted photon is of the same of the incident photon and the same phase with the same polarization, we can say. So it means that when the atom is stimulated to emit the light energy by incident wave, the liberated energy can add to the wave in the constructive manner, and this emitted light is bounced back and forth internally between the two emitting surface. So the bouncing back and forth of the light, which causes their intensity to reinforce and build up. So this results in a high brilliance single frequency light beam, providing the amplification. Emission and the absorption rate. So if the N1 and N2 are the atomic density in the ground and excited state, then the rate of the spontaneous emission is A into N2. Now the rate of the stimulated emission, that is RSTIN, stimulation, is equal to B into N2 into rho EM. Okay, so the rate of absorption is RBS is equal to B dash N1 rho EM, where A, B and B dash all are the constant and the rho EM, that is the spectral density. Rate of the absorption, that is under the equilibrium condition, the atomic density N1 and N2 are given by the Boltzmann statistics. So it is N2 upon N1 is equal to Eg whole raised to minus Eg upon Kb into T. So we can rewrite it, that is Eg whole raised to minus Hb upon Kb into T. So where the Kb is the Boltzmann constant, T is the absolute temperature, and under the equilibrium, the upward and the downward transition rates, which are same. So AN2, AN1 plus BN2 rho PM is equal to B dash N1 rho PM. So comparing the spectral density of the black body radiation that given by the Planck formula, and therefore the A and B are called the Einstein's coefficient. So this is related to the ILD. Now the next is the Fabry-Perot Resonator. So here you can see the diagram of the Fabry-Perot Resonator and how it provides the coherent beam. So this is the diagram of the Fabry-Perot Resonator cavity for a laser diode. Now these lasers are the oscillators which are operating at the frequency, And this oscillator that is formed by the resonant cavity providing a selective feedback. So, this cavity that is normally a Fabry-Perot resonator, that is a two parallel plane mirrors are there separated by the distance L. Okay, so now the light propagating along the axis of the interferometer, which is refracted by the mirrors back to the amplifying medium and providing the optical gain. So the dimensions of cavities are 25 to 500 micrometer longitudinal, 5 to 15 micrometer lateral, and 0.1 to 0.2 micrometer transverse. So this made a two heterojunctions provide the carrier and optical confinement in a direction normal to the junction, and the current at which the lacing starts is the threshold current. So above this current, the output power that increases sharply, and the two heterojunctions provide the carrier and the optical confinement in a direction that is normal to the junction. So the current at which the lacing starts, which is also referred to as a threshold current, and above this it increases the sharply. So this is regarding the short note for the ILD as well as the Fabry-Perot resonator, which provides us the sharper beam. So this way the variety of the applications that are available to make this kind of the laser. So thank you very much everyone.